see it all the time. Whenever we do experiments where we have to change the potential, we have to worry about this charging current being part of the experimental results. All right. Now, we've only talked about the situation where the current arises solely due to the charging and discharging of the double-layer capacitance. But this is not a very interesting electrochemical experiment, because usually we're interested in the reactions that occur when we have some test material in solution that we're trying to understand the rate of electron transfer kinetics of it, or we're trying to get the concentration of it by doing an analytical experiment, or we're trying to remove it by some process. So usually we have some Faradaic current in our cell. So let's consider our electrochemical cell now with Faradaic current in it. Things become quickly more complicated because our Faradaic process is not a simple resistor or capacitor signal. If it was, we probably wouldn't be having this course, because it would be easy to calculate all the cases for electron transfer processes that have been done a long time ago, and they probably wouldn't even worry about it. But because it's a nonlinear function of potential, our current that arises from Faradaic processes is complicated. And so we're going to think about our electrochemical cell with Faradaic currents effects happening. And let's take our cell, again, remember using that little circle is our working electrode abbreviation, and this little arrowhead is our, what they call a reference electrode or the counter electrode. And we've allowed ourselves now the possibility of a Faradaic reaction. In other words, some part of the system may undergo a chemical reaction. And we could see that if this was, say, a copper wire in solution. Pretty much in any aqueous solution, if we apply sufficient potential, we can oxidize that copper, especially if it has some chloride in the system. So this is what they call a two-electrode cell. Obviously, why? Because it's got two electrodes in it. There are actually three sources of potential drop. If we did this cell in a kind of a two-dimensional view, where one dimension is distance and the other dimension is potential, we could draw something like this. And we'll use our distance as a term as x. And so we're just talking about if we drew a line between our reference electrode and a working electrode, and we looked at the potential throughout that system. Now we would have in our system two phases. One would be a copper phase, and one would be a mercury phase. Now, right at the electrode interface, there is a potential drop. Oh, shoot. Let's try it here. And then throughout the solution, there is a potential drop. And then there is a potential drop at the other interface. So there's actually three cases where we can consider a potential drop occurring. So there is a V sub W, which is the drop across the interface. Why is that there? Remember, now we've allowed for the possibility of current flow. So if we have current flowing, we have to have some potential driving that process. because we're driving it from equilibrium, so we require some potential energy to do that reaction. So we're applying potential to it, and so that potential required to do that reaction is the potential drop across the interface. Likewise, we need a potential drop across the reference electrode solution interface as well. And that may be less. In fact, it usually is quite a bit less because we've specifically designed our reference electrode to have small potential drops compared to our working electrode. We usually engineer that by making our reference electrode much larger in area than our working electrode. So what's this other part here? And this is the one I just want to talk about right for now. We'll talk about those other things later. But this part here, where we have a drop across the system, that's what we call V sub S. And V sub S is going to be equal to the current flowing at the working electrode times the solution resistance. So the potential drop that we see is, if we sum up all the potential drops, we'll get the applied potential. And so it's going to be the potential drop across the working electrode interface, the potential drop across the solution, and the potential drop across the reference electrode. Now, we're only interested in this part of the potential drop across the interface, because we want to make things simple on ourselves. We don't want to have more variables than we can handle. So if we try to minimize the potential drop across the solution and minimize the potential drop across the reference electrode, that makes our life much easier. I see we're sort of at an hour's time, so I think what we'll do here is stop for a moment and take a little break, and we'll start again in, let's say, in 5 minutes or so. These topics in quite a bit more detail as we go on, so I just want to give you a flavor of some things that we're going to be doing. Okay, so what I'm saying with the, we ready to go? I guess we are. What I'm saying with the Faradaic current, now that we have the possibility of a constant current flowing through our system, or the current due to the reaction, we have to consider the fact that that current has to flow through the solution phase. Since the solution phase has a resistance to it, there will always be this IR drop, they call, or ohmic drop. You'll hear both terms, IR drop. And both of those are referring to the fact that you get current flow through the solution resistance. Ohmic, it refers to Ohm's law, which is the relationship between current, potential, and resistance. So we're trying to make these V sub R and V sub S small. How can we make V sub R small? We said we could make our reference electrode very large with respect to the working electrode. That's sometimes kind of inconvenient, but we can do it. How can we make V sub S small? Well, we can make V sub S small, or delta V sub S small, by a couple of things. One is to try to reduce the solution resistance as much as possible. And that would be by, say, adding a high concentration of an electrolyte, like an acid, or by adding a large concentration of salts. This kind of works, but for example, certain solvents like acetonitrile, you can only put so much salt in, so there's always going to be some resistance no matter what. You can also try to reduce the effect of V sub S by dropping the current. By using smaller electrodes, we can have these sorts of things. Now, in many analytical cases, we can do these and probably almost completely eliminate the effect of IR drop or ohmic drop, but for industrial important processes, we have to very much consider these two things, because often we cannot either economically add a large amount of salt to the system, or technologically, or do we want to run at low currents? We want to do the reactions rapidly, so we want to use large currents. Let's reiterate our idea on V sub R. We want to make V sub R small. The way to do that is to make our SCE an ideally polarized electrode. Okay. Okay? Remember what that means is that we have an electrode that no matter what potential we try to apply, the current flows so much that we can never really polarize that electrode potential. Now that's not true. Every real electrode can be polarized eventually if you try to apply enough potential to it. But for most cases, if we make our SCE big, we can make our SCE a pretty good polarized electrode. Again, let's reiterate what an SCE is. We have got this mercury chloride solution, which is saturated in aqueous phase because it's not very soluble, so it's easily saturated. And that is reduced to 2 mercury atoms as liquid and 2 chloride ions also saturated in solution. So this is a saturated calomel electrode. SCE, and this is calomel. What's the potential of our saturated calomel electrode? Why is it a good reference electrode? First of all, let's see that the potential is calculated by the Nernst equation, which we haven't talked about before, but we'll talk about later. You might remember it from undergraduate chemistry. The Nernst equation, which is the relationship between potential of an electrochemical cell and activities. So the activity of, what would be the activity of the calomel, which is a solid, and the activity squared of the mercury liquid, and the activity squared of the chloride.
What is that in front of the Hg2?
That's an A, and that stands for activity. Remember the activity is a term that relates the effective, you can think of it as the effective concentration or the effective chemical strength of a particular species in solution. And so rather than concentration, we would, you have to, for thermodynamically valid equations, we use activity. But remember, the activity of a solid is defined usually as 1. The activity of a liquid, a pure liquid, would also be equal to 1. And so the only thing that it depends on, the mercury calomel, saturated calomel electrode depends on for potential is the activity of the chloride species. So E is proportional to the natural log of 1 over the activity of the chloride species. And since the chloride ion is saturated in that solution because of the way we've designed it, so the potential of our reference electrode is quite stable. As long as we maintain a saturated chloride ion concentration, we get a very constant electrode potential. What happens if we try to pull some current out of our system? The Nernst equation is really only accurate for equilibrium systems. But we can think about what would happen if we try to make a little bit of what they call cathodic current drawn out of the circuit. That would be, some of the calomel would be converted into mercury by that reduction process. Like vice versa, if we try to draw some oxidative current out of the calomel electrode, some of the mercury metal will be returned back to calomel. So this particular system, if we've got enough of it, can easily supply small amounts of current without perturbing the concentration of the system. Because the chloride is saturated, we can supply all the chloride we need. It won't change the potential. These are always equal to 1 no matter how much we've got available, so we can easily maintain a constant potential. So a reference electrode used in this particular case is, for a 2-electrode cell, is important to have a large reference electrode that's got and easily maintain ideally polarized electrode behavior. Well, the potential drop in solution is inevitable, so we always have to deal with it. But that doesn't mean we can't try to minimize the effect of potential drop in solution. How can we do that? Like I said, we can make I small or R small. Can't always do that. So we can actually come up with some electronic methods and experimental methods that minimizes the effect of IR drop or ohmic drop. And the way to do that is to use what they call a 3-electrode cell. And I've drawn in our normal working electrode, and I'm going to draw in our reference electrode here. And I'm going to draw in a 3rd electrode, and this electrode is called the auxiliary electrode. And so this is our working electrode, the reference electrode, just like before. And how does this 3-electrode cell work? Well, it turns out what we do is we put in a potential measuring device between the working electrode and the reference electrode. And then we put in an amperometric measuring device, or ammeter, in there. And we can also apply some sort of voltage by some power supply, perhaps a battery, and so on. Now in this case, what happens when the current flows through the system? Well, again, current is set up, if you notice how we've set it up now, the current is going to flow between the auxiliary and the working electrode. And so the solution IR drop is going to occur between the auxiliary and working electrode. And we can think about the solution volume between those two as something like a resistor. And you might be familiar with variable resistors, which are resistors that have a tap on the resistor, let's say coils of wire, so that we can get various values of the resistor by, say, turning a knob, by varying the position of the tap along that resistor. A similar situation occurs in our cell. We can think of that as the working electrode, and that is the auxiliary electrode, and our tap is the reference electrode. What's happening now is current is flowing through the auxiliary electrode to the working electrode, and we can use our reference electrode not as a tap to get different resistances, but we can actually measure the potential of the solution near the working electrode point. So that's the point of this potential measuring device. What we're doing is we're going to measure the potential of the solution near the working electrode. Now, since we've assumed that IR drop is inevitable, what we can do is we can put whatever potential we require at the auxiliary electrode so that when we measure the potential near the working electrode, it is about what we need it to be. So if we want 1 volt at the working electrode, and when we don't have the reference electrode in there, we see that we can apply, say, 2 volts at the auxiliary electrode. Some of that voltage gets dropped as IR drop, but we can actually measure the solution by the reference electrode and see whether we've got that 1 volt actually at the electrode surface. And so what we can do is, if there is not 1 volt at the electrode surface as measured by the reference electrode, we can adjust the auxiliary electrode potential until it is. So let's suppose we're putting 2 volts here and we see 0.5 volts at the working electrode. What we can do is we can crank up our applied voltage on the auxiliary electrode, say to 3 volts, then measure the reference electrode potential again and see, well, okay, now we've got, say, 1.2 volts at the working electrode in the solution near the system. Okay, now we've got to drop that back down. So maybe at, say, 2.8 volts, we get the proper voltage on the auxiliary electrode to give us the desired 1 volt on the reference electrode. So by adjusting this potential here and measuring the potential across the working electrode and reference electrode, we can not remove the effect of IR drop, but make it so that it's not important for the process at the working electrode. Another way to do that is to draw a little diagram. Remember our diagram where we had a potential drop at the interface, a potential drop through the solution, and then another potential drop at the reference electrode. And so we can think of our reference electrode as being a tap onto that potential and trying to minimize the thing. Notice we're not completely eliminating the effect of the IR drop. There's always a little bit of a IR drop that we can't completely reduce because we can't have that reference electrode exactly at the electrode surface, but we can do a pretty good job of it. Now, I've talked about doing that sort of in a manual way by sitting there adjusting knobs and measuring the potential, but in fact you can build an instrument that does all that automatically for you, and so you can use what they call a potentiostat, which is just designed to do that job for you. It'll use a reference electrode to measure the working electrode potential or close to it, and then adjust the auxiliary potential to be what you need to be. And those can be operating very high frequencies up into the hundreds of kilohertz frequency region to get good potential control of your electrode all the time. So 3 electrode cells are very often used, particularly in synthetic type systems where we have large current flows through the system, where we want to have good, accurate potential control of the system. Use a potentiostat for that process. There's another advantage of our potentiostat, though, and that's because now we've eliminated some of the difficulties we've had with our reference electrode. Before we said we had to have the reference electrode very large so that the potential drop at the reference electrode interface is small. We don't want to have the reference electrode interfering with the potential drop, interfering with the process. But now, since we've made the reference electrode's job only that of being a potential measurement point, it doesn't have to be large and big because we're not requiring to draw any current out of that reference electrode. So it doesn't have to be a very good reference electrode compared to the kind of reference electrode you needed for the 2 electrode cell. So what's that mean? Well, we can make our reference electrode much smaller, because in the process of measuring the potential, we don't need to pull any current out of the reference electrode, and so the reference electrode can be much smaller, and that makes things much more convenient. We can make our electrochemical cells much more nicely. That also means that we can use all kinds of different chemistries for reference electrodes, ones that would not be so good for 2 electrode cells, but we can use for 3 electrode cells. One good example is what they often call a quasi-reference electrode. Quasi-reference electrode, which is, for example, something as simple as a silver wire. Now, a silver wire in a solution doesn't have a fixed potential, but as long as we're not required to pull any potential current out of it, it actually can be poised at a potential long enough to be useful in the system. Okay. All right. Well, we've kind of talked now a little bit about 2 electrode cells and 3 electrode cells. We've talked about the electric effects of having either non-Faradaic current flow through the system or flow in the system, or Faradaic current flowing through the system. So the non-Faradaic effect is the effect of the charging current that flows, and the Faradaic effect has Faradaic current has the bad effect of causing IR drop, which we have to use experimental methods to try to minimize. But now let's go back to some chemistry and electrochemistry and try to understand what's happening in the system when we're allowing Faradaic current to flow. And so let's get away from purely the electrical effects of the system.